this video, we're going to begin Chapter 8, Multiple Degree of Freedom Systems. So in this chapter, we're going to first discuss free vibrations of 2 degree of freedom systems. And in this video, we're going to go through the equations of motion, solution of the equations of motion, talk about the response in terms of normal modes, and then discuss the concept of beating for multiple degree of freedom systems. And then in the next sections of the chapter, we will talk about coupling of equations of motion, the eigenvalue problem, semi-definite systems, influence coefficients, and forced vibrations of undamped 2 degree of freedom systems, such as a vibration absorber. So first, let's discuss this idea of multiple degree of freedom systems. So up until now, we have only examined systems that could be fully described with a single coordinate. But discrete vibrating systems that cannot be described with a single coordinate are known as multiple degree of freedom systems, or MDOF systems. The simplest possible multiple degree of freedom system is a 2 degree of freedom system. But all the important qualities to understand here can be demonstrated with these simple systems. And then these these concepts can be easily extended to any degree of system. So first we're going to talk about free vibrations of 2 degree of freedom systems. So the system shown here is comprised of 2 masses and several springs. It can be considered as a 2 degree of freedom system because 2 coordinates are necessary to fully describe the system behavior. So for example, we can use x1 and x2 to describe the position of the 2 different masses in the system. Using only 1 coordinate would not be enough to fully describe the system. So 2 coordinates are necessary. Now x1 and x2, which are measured from the equilibrium positions as drawn here, can be good choices for describing the coordinates, but there is sometimes a better choice, and we will discuss that as we move forward. For now, let's consider x1 and x2 as our coordinates, which describe the position of the 2 different masses, as measured from their equilibrium positions. Now, just as an illustration, let's consider 2 specific initial displacements from equilibrium, as shown here. So first, we're going to consider, in this scenario, the 2 masses displaced equal amounts away from the equilibrium position in the same direction. So you can see both of the masses have moved a distance here, a1 and a2, in the same direction. And if a1 is equal to a2, then that ratio is equal to 1. An alternative set of initial conditions is that both masses are displaced the same amount. So again, a1, the magnitude of a1 and a2 are equal, but this time they are both displaced in the opposite direction. So they're both kind of brought together and the center spring becomes squished. So in case A, as I said, the 2 masses are displaced the same distance in the same direction so that the spring between them is unstretched. This would mean that the center spring has no effect on the resulting motion, so it's as if the spring was not present, and so we could represent the system as shown here, without the spring in the middle, because the spring was not stretched at all. If these 2 identical masses are initially displaced with a1 is equal to a2 and released from rest, they will both vibrate with a frequency of p1, which is equal to the square root of k over m. So you can see that if both m's are the same, and both k's are the same, and they're both displaced by the same amount, then they will both have the same natural frequency, square root of k over m. So this is similar to 2 single degree of freedom systems that happen to be operating exactly in parallel. But because it doesn't restrict the possible motion of the system, it's still considered a 2 degree of freedom system, because we still are using those 2 different coordinates to describe the motion. Now in case B, the 2 masses are displaced by equal amounts, but in opposite directions. So the central spring compresses, but because of symmetry, we can actually consider the center point of that spring like a fixed point. So we could represent it like something like this, where the center point here is like a fixed support. Now the fixed boundary in the center behaves effectively as a stationary point, and the effective spring constant on each side becomes greater because shorter springs are stiffer. So the masses are supported by two springs in parallel, so the natural frequency becomes the square root of k plus 2kc over m. So we'll call this one P2. So to summarize, for this 2 degree of freedom system, we have two potential natural frequencies that occur depending on the initial displacements. So when A1 equals A2, and when A1 equals negative A2, we have two corresponding natural frequencies. P1 is equal to the square root of k over m, and P2 is equal to the square root of k plus 2kc over m. So this was an illustration to show the response with these two specific sets of initial conditions. And now we'll go through how we actually go through the analysis with the equations of motion and solving those equations for a multiple degree of freedom system like this one. So we've selected our coordinates x1 and x2. We need to find the equations of motion that describe the system. So usually we have one equation per coordinate of the system. So in this case, we will expect to need two equations of motion. So just as for single degree of freedom systems, we're going to start with the free body diagram, mass acceleration diagram. So for mass 1, we can draw our free body diagram, mass acceleration diagram as here. So if we say that x1 was positive to the right, then the force in the spring on the left is going to be K1 x1, and then the force in the spring in the center is going to be Kc times x2 minus x1, which is basically if we assume that x2 moves more than x1, so let's draw our system again. We had this spring between them. So this was our x1, and this was our x2. This is k, k, and kc. So here, basically, if we assume that this spring is in tension, or assume that x2 moves more than x1, then the force in that, or the stretch in that spring is x2 minus x1, so the force in that spring is kc times x2 minus x1. And then, the mass acceleration diagram is just mx1 double dot. Now, the important thing is when we go to draw the free body diagram of the second one, that this force needs to be equal and opposite on the other free body diagram. So it's very important that we draw things displaced in the positive coordinate direction, and when we make this assumption, that we stick with it and draw this equal and opposite on the other mass that it's connected to. So in this case, x2 is also positive to the right. So the force, the spring over here is going to be pushing it back to the left with the force kx2, and then we've got this force in our spring connecting the two of them, which again is equal and opposite on the two free body diagrams. So applying Newton's laws to the first mass gives sum of forces equals ma. We've got minus kx1 plus kc x2 minus x1 is equal to mx1 double dot, which we can rearrange as shown here. And for mass 2, we get sum of forces equals ma. We get this minus kc times x2 minus x1 minus kx2 is equal to mx2 double dot, which we can rearrange as shown here. So the two equations of motion for the system are mx1 double dot plus kc x1 minus kc x2 equals 0, and mx2 double dot minus kc x1 plus k plus kc x2 is equal to 0. Now, it's more convenient to write these out in matrix form. So this introduces the concept of mass and stiffness matrices. So we can rewrite these equations as a single matrix equation. So this is our mass matrix, and this is our stiffness matrix. So it's important to realize that these equations are coupled. So x1 and x2 appear in both equations. So this means that x1 and x2 cannot be solved for independently, but must actually be found together. So we need to solve this single matrix equation, or these two individual equations, simultaneously. So let's talk about the solution to the equations of motion. So to solve for these equations, we look for solutions in which the masses are undergoing harmonic motion at the same frequency. So we call this simple simultaneous harmonic motion. So we assume that the motion of the masses is of the form x1 of t is a1 sine pt plus phi, and x2 of t is a2 sine pt plus 2 sine pt plus phi. Or we could rewrite this as x1, x2 is equal to a1, a2 times sine pt plus phi. So you see that both of these are undergoing this harmonic motion at the same frequency, so simultaneous harmonic motion. So this is, we assume that this is the form of the response, or the form of the solution. So for this equation, a1 and a2 are the amplitudes of motion for m1 and m2 respectively. So those are our masses. And x1 and x2 describe the positions of those masses, if you recall our coordinates. So with this assumption, it follows that we can calculate the acceleration by taking the derivative of this expression twice. And then we can substitute these values into the equations of motion. So what we get is this here. So this is the, this was mx double dot plus kx is equal to 0. And we can bring these, basically factor out the a1, a2 sine pt plus phi. And then now we can combine these two matrices together, just add them together, and we get this equation here. So this must be true for all times t, which means that this is not necessarily 0 for all times t. So that means that this must be true. So this matrix, which is the combination of our mass and stiffness matrices, multiplied by our vector of amplitudes, is equal to 0, or the 0 vector. Okay, so now we've got this equation here. So there's two possibilities that satisfy this. a1, a2 could be equal to the 0 vector. This implies that there's no motion, so this is the trivial solution. The other option is that the determinant of this matrix is equal to 0. So basically, that this matrix does not have an inverse. This is a requirement from linear algebra for this equation to have a non-trivial solution. So the determinant of that matrix has to be equal to 0 for us to be able to find a non-trivial solution. So we've got a 2 by 2 matrix here, so we can write down the form of the determinant. So if we have this 2 by 2 matrix with, let's call the entries A, B, C, and D, then the determinant is AD minus BC. So for our equation, or for our matrix, this determinant is can be written out in this form. So this is our A, our D, our B, and our C. Now we can multiply this out to get the equation shown here. And we can simplify this, and we see that we get this quadratic equation in p squared. So with a p to the 4th term, and then a p squared term, and then a term with no p's. That in the end, you can also see that it depends on our mass and our stiffnesses. So this is known as the characteristic equation for the system. So this characteristic equation, as I said, is a quadratic equation for p squared. So we can use the quadratic formula to solve this, to find the two values of p squared that satisfy this. And we can simplify this down, as you can see, and we get these two values for p squared. So p1 squared is going to be k over m, and p2 squared is k plus 2kc over m. So you can see this is the same natural frequencies that we got when we just considered those specific set of initial conditions. So these equations, or solution, gives the two natural frequencies of our 2 degree of freedom system. The order of the frequencies is arbitrary, but it's customary to order them from lowest to highest. So P1 is the lowest, or the fundamental natural frequency, and then P2 is the second natural frequency. And so because we have a 2 degree of freedom system, we have two equations, we expect to have two natural frequencies. So if we have a higher number of degrees of freedom, then we have a higher number of natural frequencies. So in general, if we have an n degree of freedom system, we will have to solve for an nth order polynomial characteristic equation to find the n natural frequencies. So once we've found our natural frequencies, we can use them to find a1 and a2 in our equation. So recall this was our equation for the response of the system. So far we've only found p. So we need to do a little bit more work to be able to get the whole response of the system. So we can use equation 8.4 to find a1 and a2. So this was our equation 8.4. Because the matrix is singular for the two values of p squared that we found, we can't find a unique solution for a1 and a2, but we can find a relationship between them. So the first natural frequency that we found was p1 squared was equal to k over m. So we can substitute that into our equation and then simplify, and we get this equation here. So this gives us two equations that we can use to solve for these values. So if we take the first equation here, we see that a2 over a1 is equal to 1. If we take the second equation, we get the same result. a2 over a1 is equal to 1. So these results show that it doesn't really matter which of the two equations are used. We can't get a unique result. We can just get the relationship between a1 and a2. Now, if we use the second natural frequency and substitute that into our equation, then we get the expression here, and we can simplify this to get this equation. And now, the first of these equations now gives that a2 over a1 is equal to negative 1, and the second of these equations gives that a2 over a1 is also equal to negative 1. So again, the choice of the first or second equation doesn't matter when obtaining the ratio of the amplitudes, because again, we can't get a unique solution to find both a1 and a2. We can only get this relationship between them. But it's important to see that the ratio is different for each of the natural frequencies of the system. So we need to do this for each of the natural frequencies. So to summarize, for this system, we have P1 is equal to the square root of k over m, and a2 over a1, 1, is equal to positive 1. We have P2 is equal to the square root of k plus 2kc over m, and a2 over a1, 2, is equal to negative 1. So we typically arbitrarily assign an amplitude of 1 for one of the amplitudes. So for example, we can say that a1 is equal to 1. So then we can say basically that our a2 over a1, 1 is equal to 1 if we assume that a1 is equal to 1. For the second natural frequency, we can do the same thing, and we see that a2 over a1, 2 is equal to negative 1. So the results can be represented with these expressions. So a1, a2, this vector, a1, a2, 1, can be the vector 1, 1, and a1, a2, 2 is the vector 1, negative 1. So the response of the system in the first and second modes is now written like this. So this is the first mode, and this is the second mode. So these terms A2, this vector, A2, A1, A2, 1, and A1, A2, 2, we can call phi 1 and phi 2. These are known as the first and second mode shapes, and they're also known as the normal modes of the system. So often the normal modes are normalized to be represented as a unit vector. So we could write them as shown here. So 1 over the square root of 2 times this vector 1, 1, or 1 over the square root of 2 times the vector 1, negative 1. So far we've found both the natural frequencies and the mode shapes for our 2 degree of freedom system. And each natural frequency has a particular mode shape associated with it. There are many ways that the mode shapes can be represented. So we don't need to normalize them to be unit vectors, but we can. There's lots of different ways that we can do it. The important thing is that about them is that the ratio of the various amplitudes that they represent. So it's quite often useful to represent the response in terms of these normal modes. So normal modes can be used to represent the response of the system. So for each natural frequency, there's an associated mode shape. The system of equations is linear, so the total solution can be found by superposition of the two individual solutions. So adding the two solutions gives the following result. So we can see that our vector x1, x2 of t is going to be our first mode plus our second mode, which we can write as shown here. So basically representing these with the amplitude times our mode shape, amplitude times our mode shape, and now we see this one has our first natural frequency and our second natural frequency. And we've also got this phi 1 and phi 2 for our two different modes. So this is the first mode response and the second mode response, and the total response is just a linear combination of the two modes. So A1 1 and A1 2 represent the actual amplitude of mass 1 in the first and second modes, respectively. Within each mode, the masses reach their maximum and minimum positions simultaneously and pass through equilibrium simultaneously. So the equation 8.14 can be rewritten as shown here, where P1 is equal to the square root of k over m, and P2 is square root of k plus 2kc over m for our particular system. So you can see that we have four arbitrary constants, A11, A12, phi 1, and phi 2. The scalar values, A11, A12, represent how much of the mode is present, while the other scalar values, phi 1 and phi 2, represent the relative phase angle between the modes. We can rewrite this further, as shown here, and as we've seen for single degree of freedom systems, we could rewrite each of the modes, instead of an amplitude and a phase angle, we can write it as an A sine pt plus a B cosine pt, and C sine p2t plus D cosine p2t. So this is the same, but with four constants A, B, C, and D, which it can be determined by the initial conditions. So initial conditions are typically found from the initial position and velocity of each mass. So we can say define some initial position and initial velocity for each of our masses. With these initial conditions, our equation at time t equals 0 gives that the expression for B and D in terms of the initial positions. And we can differentiate our equation to get the velocities, and using the initial conditions for our velocities, we can find the expressions for A and C. So now we found all of our arbitrary constants in terms of our initial conditions. So combining these results, the total response is given as this expression here. If we use the form with the amplitude and phase angles instead, we can note what the amplitude and phase angles are. for both A11 and A12 and phi1 and phi2. So to see how these responses can be used, we can consider some specific initial conditions. So first let's consider that x1 0 is equal to x0, x2 0 is equal to x0, and both masses start from rest. So both masses are displaced in their positive directions by the same amount and start from rest. So the response then becomes this expression here, because B is equal to x naught, and A, C, and D are all equal to 0. So this shows that the response is made purely of mode 1, because we only have our cosine P1 of t here. The masses move together with the same frequency in the same direction, and the center spring remains undeformed. With these initial conditions, so now x1 moves a distance x0, x2 moves a distance x0 but in the opposite direction, and again we start from rest. The response becomes only in the second mode, because D is equal to x0 now, and ABC are all equal. And ABC are all equal to 0. So this shows that the response is made of purely the second mode. The masses move together with the same frequency and amplitudes, but in opposing directions, and so the center of the central spring doesn't move. So the previous results demonstrate that the response of linear multiple degree of freedom systems will always be a linear combination of normal mode responses of the system corresponding to each natural frequency. The amplitude and phase angle of each mode are determined by the initial conditions. So this is the fundamental idea behind the approach known as modal analysis. The mathematical approach agrees with the physical reasoning that we got from our illustration at the beginning of our analysis here, for those specific situations that we considered, which put us into those pure modes. But this approach generalizes the system and allows us to represent the system for any initial conditions. So this will become more important as the physical systems get more complex. Now, we can talk about the concept of beating. So when we looked at a forced single degree of freedom system operating near its resonant frequency, we saw this phenomenon. A similar behavior can be observed with two degree of freedom systems with two natural frequencies that are close to one another. So let's consider a 2 degree of freedom system with these initial conditions. So we're just displacing one of the masses with some initial amplitude x. The other mass is not being displaced, and both of the masses are starting, or both of the coordinates have a zero initial velocity. So with these initial conditions, we can find that our constants, A is equal to 0, B is x over 2, C is 0, and D is x over 2. So the response will become this expression here, and so the response of each of the masses is given as shown here. So we have the response of the first one is x over 2 cosine p1t plus cosine p2t, and the response of the second is x over 2 cosine p1t minus cosine p2t. So we can use trig identities to convert these to these expressions. And this is valid for any p1 and p2. So now, if p1 and p2 are close, then we have p2 minus p1 is 2 delta, where delta is a small number. So this means we would have, we can rewrite our equations as shown here, where we're replacing that p2 minus p1 over 2 term with this delta, this small number. So this can be interpreted as vibrations occurring at a frequency of p2 plus p1 over 2, and the amplitude of the vibrations varies at a frequency of delta, which is very small. So essentially this is the amplitude of the vibrations at this frequency, and so this amplitude varies with this very small frequency. And so the beating frequency is 2 times this small frequency, so 2 delta. And the beat period is 2 pi over 2 delta, or 2 pi over 2 p2 minus p1, and is the time between the minimums and the maximums. So let's just look at a few, put in some values, and to see what this looks like. So with these values, we would get a response that looks like this. So x1, this is showing x1 and x2, and you see we get this combination where we've got this high frequency component, and then the amplitude of it varies at this much lower frequency. So we can see that the energy is transferred from one mass to the other and back. It's a conservative system, so the total energy is constant. So basically you can see that this value, this mass, is at its highest, or is moving the most when this one is not moving at all. And then as this one, the amplitude goes down to 0, this one reaches its largest amplitude. So basically the energy is transferred from one mass to the other and back.